for this work, what is the one important term? What is your important term? Maybe I will make some scoring, for scoring. This is a criteria to decide your score. What is the important word, keyword? 何でしょう? What is the important keyword about the medical waste problem?
Infection.
Infection はもちろんインフェクションでクレイルとかオービングというね。あと何でしょう。それさっきのビデオでやっていたこれですね。ディスポーザブルですね。ディスポーザブルっていうのはone important ディスポっていうディスポーザブル because of the disposable tools, disposable materials, so therefore it makes a medical waste problem. Easy to use, easy to spend, but sometimes it is difficult to treat. それあるじゃん、problem. Medical waste problem っていうのは For example, the injection need. In some cases, it is affected by some viruses or some other bad something. So therefore, it is necessary to treat the sterilization because of kill the viruses by high temperature treatment or electromagnetic waves irradiation. And after that, it is enclosed into some plastics or some blocks. And then it is again melted down or the inclinations. So, and then it is used as a material again or it is landfilled as scraps. Medical waste problem. To prevent that kind of viruses or some AIDS problems. But this kind of disposable is like これだよね。例えば for example the polyvinyls or some other plastic bags like this or some tubes is easy to use. So therefore, in many countries, not only the developing country is also using this kind of tools, this kind of materials. They're easy to use because this is ここに書いてあるけど、easy to molding, it is easy to fabricate, manufacture, and the very, very low cost because of vinyls. So therefore, they're easy to use. But it is only once used. It must not be used again. So therefore, it makes medical waste. そう、ここに書いてあるように、blood transfusions, infusion solution bags or tubes or the artificial organs, artificial kidneys, circuit, and so on. This makes the ここに見ていいですか? ローブスとかもね、まあこういう all of them becomes a medical waste ということで、なんかさっきビデオ見ましたけど、we have watched some videos to prevent from the not only the medical professions, healthcare professions, housekeeping, but also the medical waste is sometimes discarded or some illegal dumped into some other lands or some rural places wasted illegally. So this makes some for example environmental affection, pollution, environmental pollution or some other contaminated, environmental contamination, it makes. So therefore the correctly and surely treatment is required. Is those videos showing that kind of treatment. The product control is also necessary. The waste processing is necessary. So therefore this is one of the highlights of the last week's contents. Okay. それはどの辺にあったかというと、この、だからマテリアルのところに、メタリックマテリアルとかインオーガニックマテリアルとかあるんだけど、ポリマーマテリアルっていうのが、まあ、it is very familiar and widely used presently from the oils or some other materials is used. So it is easy to produce. It is easy for shaping some target shape. So therefore it is widely used presently for the medical materials as the medical materials. ということで、ここに、高分子材料、ポリマーズ、some polymers, disposable meat products for surgical instruments and so on. The other highlight is maybe last week's contents. One important keyword is これ例えばこれね、biocompatibility これね、biocompatibility is general keyword about last week's contents. Biocompatibility それはまあなんかティッシュ、ヒストコンパティビリティとヘモコンパティビリティ、ブラッドコンパティビリティがあって、まあso therefore the blood compatibility is one important part. ブラッドコンパティビリティがどこにあるかっていうとこれだ。それはマテリアル、これアーティシャルマテリアル is contacted with some blood. It makes some various reactions、ね、それはプラズマプロテインのアブソープションとかブラッドウェットアドヒーチョンとかアグリゲーションとかアグリゲーションとかディフォーメーションでブラッドコアギュレーションでファクター is the vitalized. So therefore the blood clot thrombus is made and in some cases calcium is deposed. Okay? And then it makes effect to the, for example, it closes. It makes a close in the blood circulation system, or the artificial organ cannot work exactly, correctly by the calcium deposition and so on. So therefore the blood compatibility material is very important. Blood clot, what is blood clot は Yes, まあこれは go back to today's part ということでいいですかね。それでSo therefore the heart, we discussed today about the heart. Okay? じゃあ、let's go back to today's part. Heart ですね。これで、 これどうやってますか？これはハートファンクションitselfと、エレクトルカーディオグラムカーディアックサイクルっていう、まあ、これは、まあ、シグナルとかいう話ですね。And then the engineering analysis っていう話ですね。だから、first part is medicines and the second part is まあ、bioelectronics and the third part is まあ、mechanical part ですね。mechanical engineering。はい、じゃあ firstly about the heart。heart is なんか some kind of pump。これは returning part で、go to the lung and this part is from lung and then go to the entire bodies ということで、in mammals and some birds is to heart. There are totally four chambers here. ちょっとなんかこれ見てみますか？
Hi, welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to describe the structure of the heart. You should then be able to describe how the heart pumps blood around the body. We're going to start by looking at single and double circulatory systems. Fish have a single circulatory system. The oxygenated blood is pumped from the heart to the gills, where it collects oxygen and becomes oxygenated. This oxygenated blood now passes straight to the organs, where it loses its oxygen and then returns to the heart. The problem with this system is that the blood loses a lot of pressure as it passes through the gills before reaching the organs. Humans, however, have a double circulatory system. Here, the oxygenated blood is pumped from the heart to the lungs, where it collects oxygen. This oxygenated blood then returns to the heart. The heart now pumps the oxygenated blood to the organs, where the blood loses its oxygen. The blood now returns back to the heart. Okay, let's continue by looking at the structure of the human heart. This shows a simplified picture of the heart. The heart is an organ consisting mainly of muscle tissue, and the job of the heart is to pump blood around the body. You need to learn the details of the structure of the heart. The first key fact is that the heart has got 4 chambers. At the top, we have the left atrium here, and we've got the right atrium here. At the bottom of the heart, we have the left ventricle here, and we have the right ventricle here.
まあ、アトリアムっていうのは storing the blood ね、storing the blood and the ventricle がまあ mainly the pumping これが storing and pumping なんですね。
You can see that the atria are separated from the ventricles by valves, and we'll take a closer look at those later. You'll notice that the heart appears to be back to front. That's because diagrams of the heart always show it as if you're looking at a person.
So therefore the storing and pumping, so therefore this valve part is very important. Valve is very important.
There are 4 main blood vessels entering and leaving the heart, and again, you're expected to know these. The vena cava brings in deoxygenated blood from the body. The blood passes from the heart to the lungs and the
skip. で、ということで、in the human heart is the body's left side and the little bit larger than the fist, your fist. Size is about your fist and a little bit larger. で、two circles ですね。で、これは This is a cross section of heart. Cross section of heart. この right side here is a この smaller. So this part, left side is more larger. Left side is more larger, and this muscles is more large muscles. around here because it takes the go to the entire bodies, the blood provide to the entire bodies. So therefore the stronger muscle is around here, okay? And this is only for the lung. So therefore it is a thin muscles here. So therefore the right heart side system and the left side system, left heart system is not equal, but the blood output average is almost equivalent, but the workload is very, very different. ね、なんかさ、ワークロードってさ、pumping to entire body っていうと、more resistance で、resistance to only for the lung is a very simple work, but to the entire body is more resistance. So therefore it makes この left side is more working harder is required. More harder work is required. だから、blood flow is almost similar, of course. This is one circuit. So therefore the circulation blood flowing amount of flowing blood is almost similar, all of them. But the workload is very, very different. それはこの internal pressure is also different. これ right side is only 15 or 20 millimeter Hg, but the left side is about まあなんか5 times or 10 times is pressure is required. High pressure, so therefore making the high pressure muscle is become larger. ということですね。次、バルブはこの this part のバルブと this part バルブ this part バルブ is a little bit different. だからですね、ここの、4チェンバーって言ったけど4チェンバーって言ったけどこことこことこことここなんだけどここのチェンバーとこのだからこれに対してインサイドインプットチェンバーインプットバルブとアウトプットバルブこれにもインプットバルブとアウトプットバルブっていうことでインプットバルブとアウトプットバルブなんですけど、インプットバルブはこいつですね。インプットバルブはこれか。これだ。これとこれか。三線弁ってやつですね。三線弁っていうやつと双方弁っていうやつで、インプットバルブはこれか。インプットバルブとアウトプットバルブです。インプットバルブの方は、こういうふうになってます。インプットバルブ。なんかこういうでここが閉まる closing by using this muscles この this valve leaf っていうところが close この output valve は this kind of valve 2 or 3 leaves is there and if it is exhausted it is generated and then the closed like this is looks like the pocket and then the closed different shape これはインプットはここからインプットしてこの inside and the back side the blood is flowing here and closed blood is flowing and closed this is the inside input valve of this pumping chamber and this is the output valve for the pumping chamber. Output is here and exhausted and then the closed like this. 2 or 3 leaves is there. ちょっとこれもちょっとなんか見てみますか。アニメーションビデオか。
The heart is the beating muscle that pumps blood throughout the body. Inside the heart, 4 valves direct blood flow. 2 valves control the flow of blood from the upper chambers, or atria, to the lower chambers, or ventricles. 2 other valves control blood flow from the ventricles to the lungs and to the rest of the body. During a normal heartbeat, the left ventricle pumps oxygen-rich blood through the aortic valve to be distributed throughout the body. A healthy aortic valve has 3 cusps that open widely to allow blood flow during ventricular contraction. The cusps then close tightly to prevent backflow during ventricular relaxation. Aortic stenosis is a condition whereby the aortic valve becomes narrow, stiff, or thickened. This severely blocks the flow of blood coming from the ventricle.
in this case it's not closed.
Aortic regurgitation is a condition that arises when the aortic valve weakens and does not close completely, causing blood to flow back into the left ventricle. With both conditions, the heart must work harder to push the same amount of oxygen and blood to the rest of the body. This may lead to heart failure. When the valves do not work properly, they must be repaired or replaced.
これはちょっとリプレイスバルブだからちょっと話は後にしましょう。はい、ということでバルブワーキングですね。で、ブラッドサーキュレーションでトゥーサーキュレーションって言いましたけど、このラングのサーキュレーションとあとエンタイアボディのサーキュレーションがあるって言いますね。ラングサーキュレーションとエンタイアボディサーキュレーションがありますって言いましたね。あとでもthe third blood circulation は also providing the blood to the heart muscle itself. ね? Heart muscle itself. So this is providing the energy, providing the blood to the heart muscles. ね? So this is right side と left side. Two main このコロニートランクって書いてあるんですけど、ライトコロナリーアーテリー。Two main artery is there. The right side and left side. Especially the left side, it is the main part of the providing the muscle, providing the heart muscles. So therefore, the left anterior descending and the left circumflex artery, it is set. And the heart attack ってありますよね。heart disease makes when this in this part, in these muscles, these blood, it is closed by some clot or thrombus. So therefore, some blood is not provided to the heart muscles, and then it is become weak, and in some cases, some muscle become dead. So therefore, it makes heart attacks. これがアンジナペクトリースとかマイオカーディアックインファクションっていう。The two muscles, the blood supply will become short, and then the muscle cells become necrotized. ね。っていうのがどっかに例えば、オーバービューオブザコロニカルディジーズとか見てみますか。
The heart is fed by its own circulation, known as the major coronary arteries. These arteries include the left anterior descending artery, the left circumflex coronary artery, and the right coronary artery. The bloodstream contains red blood cells, which deliver oxygen to the heart muscle, known as the myocardium. It also contains fats or lipids, known as low-density lipoproteins, or LDL cholesterol. Atherosclerosis begins when LDL cholesterol accumulates in the arterial wall, forming a plaque. Over time, the plaque becomes larger. Some plaques never obstruct the coronary blood flow. The patient with asymptomatic coronary disease has no chest pain and no myocardial ischemia. A plaque can enlarge to the point that the blood flow is compromised. The patient may have chest pain, but only with exertion. This syndrome is known as stable angina and is not a clinical emergency. Such a patient is still at risk for an acute life-threatening event because a plaque can suddenly rupture, causing clotting of the artery, known as coronary thrombosis. When a thrombotic occlusion is subtotal, an acute coronary syndrome develops, and there are two types. The first type is known as a non-ST segment elevation myocardial infarction, and the second type is known as unstable angina. With these syndromes, the patient experiences chest pain at rest, and the electrocardiogram shows ST segment depression. In contrast, when the thrombus completely occludes the vessel, the myocardium is injured, and the syndrome of ST segment elevation myocardial infarction develops. In summary, patients with coronary artery disease may be asymptomatic, they can have stable angina, or they can suffer an acute atherothrombotic event. Plaque rupture with coronary thrombosis is the most common cause of acute, life-threatening coronary artery disease. Emergency therapy by thrombolysis, angioplasty, or thrombectomy restores blood flow by targeting the thrombus, either dissolving it, displacing it, or removing it as quickly as possible. Rapid restoration of blood flow relieves symptoms and minimizes myocardial damage.
カーディオダメージって言いましたけど、だからなんか、この、if it is closed, the urgent treatment is necessary. In some cases, it should be melted by some drugs or some removing by some the needles or some kind of medical tools is inserted here and remove these plaques. Or it should be replaced to the bypass surgical treatment is necessary. Or new blood tube is attached to here to provide the blood to here from other part, from lung or some stomach, and some blood tube is attached to here to when this is a blocked part. This is attached to from some other places, and then provide a new circuit and generate new circuit, blood circuit. So therefore, some kind of treatment is explained later, following weeks. はい、というわけでこれがなんかドローイングして。The next is why this heart is beating. This heart is beating. Heart muscle cell is heart muscle cell is これだ。これね、cardio-myocyteっていうこの this heart muscle cell is beating by itself. They no providing anything, but this kind of a cell is making the self vibration by itself. No signal is given here, but this kind of moving is made by itself. This is a test for this is a crunched, and this is also the crunched, but it is pinched by some torsion bar, and then the displacement is measured, and how much force is generated by this muscle is this cell is measured by this cantilever's strain gauges. So therefore, the one single cell generated which kind of displacement, and which kind of force is generated by a single muscle cell is measured. So therefore, each cell is making contraction itself, of course. But if it is not coordinated, synchronized, it is no good for the pumping functions. So therefore, the coordination system, control system is necessary. Control system is necessary to make the synchronization of heart beating. So therefore, this impulse conducting system is there. The electric signal is generated here, and it is transferred like this, and then it is transferred by this following along to these fibers, and then this electrical signal is firstly generated here and transferred here and transferred here, and then from this part, and then this part, and then this is pumping functions is entirely realized. それがここに書いてあります。それがここに書いてあって、それはどんなんですかって言ったらちょっとこれ見てみますか。
The heart's conduction system controls the generation and propagation of electrical signals, or action potentials, that cause the heart's muscles to contract and the heart to pump blood. This electrical activity can be measured at electrodes placed at specific points on the skin, from which a composite recording is produced in the form of a graph. This recording is known as an electrocardiogram, or ECG, sometimes referred to as an EKG, a tracing of the overall electrical activity of the heart, resulting from the propagation of many action potentials. Let's look at what happens during a single beat of the heart and how these events are depicted on an ECG. In a normal heart, each beat begins in the right atrium with an action potential signal from the sinoatrial or SA node, the heart's natural pacemaker. The signal spreads across both atria, causing the muscle cells to depolarize and contract, inducing a phase known as atrial systole. On the ECG, this atrial depolarization is represented by the P wave. The period of conduction that follows atrial systole and precedes the contraction of the ventricles is depicted on the ECG by the PR segment, a flat line following the P wave. When the signal leaves the atria, it enters the ventricles via the atrioventricular or AV node, located in the interatrial septum. It enters the bundle of His and spreads through the bundle branches and the large diameter Purkinje fibers along the ventricle walls. As the signal spreads through the ventricles, the contractile fibers depolarize and contract very rapidly, inducing ventricular systole. The ECG's QRS complex represents this rapid ventricular depolarization. Atrial repolarization also occurs at this time, but any atrial activity is hidden on the ECG by the QRS complex. Finally, as the signal passes out of the ventricles, the ventricular walls start to relax and recover, a state described as ventricular diastole. The dome-shaped T wave on the ECG marks this ventricular repolarization. On the ECG, the ST segment depicts the period when the ventricles are depolarized. The QT interval represents the time it takes for both depolarization and repolarization of the ventricles to occur. The sequence of events just described and the associated ECG trace repeats with every heartbeat. Remember, an ECG is not a tracing of a single action potential, but an amalgamation of the many action potentials that constitute the electrical activity of the heart.
ということで、
A trait
だからこっちが This storing chamber become shorter, become smaller, and then it is pushed here, and the main part is pumping. っていう。So therefore, this kind of waving, moving,
ventricles are
movement.
depolarized. The QT interval represents the time it takes for both depolarization and repolarization of the ventricles to occur. The sequence of events just described and the associated ECG trace repeats with every heartbeat. Remember, an ECG is not a tracing of a single action potential.
というわけでした。というわけがこれで、これで、これですね。だからここの、ここから始まって、This is a starting node. で、here で、once it is concentrate again here, and then it moves like this. So therefore, this part and this part, this part and this part, and relaxed. というのが repeatedly. And this part and fasten here, P. And this part is QRS. And then the relaxed part is here. これはカーディアックサイクルですね。カーディアックサイクルです。はい。というわけで、心電図検査、Electrocardiogram examination って、when you are the healthcare checking once a year, you will make some electrode attached here and detecting your cardiac activities. And then from this ECG, what found? The illegal heartbeat is you can find. The illegal heartbeat is sometimes illegal heartbeat is here, and the more frequent heart beating is here. Or in some cases, it is not the cycle here. So therefore, these three types of the illegal heartbeat is you can find. When it is detected, why it is caused? Because of the shortage of the heart blood providing. So therefore, in some cases, heart disease is there. And also the heart is too much muscular because this workload resistance is too much resistance is there. The heart should provide blood. So therefore the heart become more stronger and more stronger. So therefore the sports athlete is becoming the heart wider, larger in some case. For normal person is like the fist size, but this patient, cardiomegaly patient become more double or twice size it becomes because too much. So high pressure, high blood pressure is no good. High blood pressure makes the high resistance for these pumping functions. So to deal with this high pressure of the blood, the muscle become more wider, more larger, and more stronger. So therefore, it makes much workload for the heart pumping function, and then it makes weak or the short lifetime of the muscles. And other muscle diseases is there, as heart disease is there, For example, the valve failure, valve disease, ね、cannot close correctly or cannot work exactly. So the electrocardiogram examination is, in some cases, most cases, is this kind of the comfort conditions, calm conditions. But the some workload is given here. So, for example, the bicycle riding, and then the treadmill running, and then this cardiac electrocardiogram is measured. And Holter monitor is a personalized handheld monitor system is attached, and daily activities, in daily life, the heart activities is measured. これは、まあ、this is a Holter measurement instrument like this. ちょっとこれが動くかどうか知らないけど、これがなんかトレッドミルってやってる時ですね。これで、まあ、このハートビートをチェックしてますね。それからこれは、これはなんかバイスクリンしますね。とか、これはもちろん、ラングコンディションも is also monitor。Breathing condition is also monitor. これはなんだ、ウルトラソニックですね。ハートビート is monitor ですね。Also the valve movement is also monitor ですね。でそれからこれはなんだ。これは MRI ですね。ということで、various examination method、Holter monitor は is here。トレッドミルとか、バイシクリングとか、このカーディオパンピング、エクササイズテスティングとか、エコーとか、ウルトラソニックシステムユージングとか、MRI、マグネティックレソナンスイメージングメソッド is also provided。ですね。で、次のがカーディアックサイクルで、さっきのEMG、ECG っていうのはこういう感じで、ハートビート。まずはファーストパートで、セカンド、メインパートでリラックスっていうのがあるんだけど、他にも、そうだ、プレッシャーか。プレッシャーはどうなりますかって言ったら、もちろん、ここで、become smaller, the pumps, pumps become working, so therefore this becomes a high pressure like here. こういう感じですね。で、あと、ハートサウンドってありますね。ハートバイクサウンド。You can hear your conditions. これ、なんか、ドックンとか言いますよね。What is a ドックンソース ?What is this sound source? What makes your heart sound? この moving makes the sound. Heart motion makes sound. Or what makes the sound? This sound.
Blood move.
え
Blood flow.
blood flow. Blood flow makes the sound. Blood flow makes sound. But another idea? Blood flow もキュルキュルっていうかmakes sound. Yes? ブラッドサウンドはどうしてできるでしょう。ブラッドサウンド、このブラッドサウンド、ハートサウンドって何でしょう。ハ ハートサウンドはメインリーのバルブクロージングですね。バルブクロージングがメイクサウンド。これはドックンドックン。このクローズする音ですね。です。というわけで、ポンプのエナジー、ポンプのキャラクタリスティックですね。プリロード、アフターロードとシストニックボリュームっていうのがあるんだけど、まあ、ハートレイト、ビーティングフリーケンシー、ビーティングレイトって書いてあるんですね。と、アウトプットパーミネット。How much milliliter, how much liter is output per minute っていうのがあって、でこれがまあ this part is a working workload of the heart muscle. And during the quiet time, the calm conditions, it is about the output of the cardiac muscle. Heart output is about the 5.5 liter per minute. This is similar to the tap water's flow. Tap water's flow looks like the 5.5 liter per minute. So much blood is provided per minute. 5.5 リッターですよ。これは1リッターボトルが1、2、3、4、5ですよ。そのくらいの blood is exhausted from the heart every minute. で、when you are exercising, it is become 4 times to the 5 times per minute. And the beating rate is also the 2 or 3 times. So, and of course, one beating, the exhausting quantity of the blood is also increased. So therefore, the totally, the 4 or 5 times compared to the usual conditions. And some athlete is when he has to work harder, more than 5 times of the blood is provided to the entire body. ちょっとこれはいいか。で、ファンクショングラフってスターリングズローはベンティキュラーのワークロードと、レフトアトリアルのプレッシャーがなんかまあディペンデンス is there。ちょっとこれなんか見てみますか。マスタープリロード、アフターロードっていうのを見てみますか。
Welcome to Master Your Medics video blog. Today we're talking about preload and afterload. Okay, so preload and afterload are actually somewhat complicated topics at first, and once you get them, they make a lot of sense. But it's actually quite important to understand them. So I'm glad you're here and you're trying to learn about what it is, because it definitely is important. So we're going to talk about stroke volume first, and then we'll make our way into preload and afterload. So I think that is important. So stroke volume is the volume of blood pumped out of the heart with each beat. Okay, the volume of blood pumped out of the heart with each beat. Okay, so roughly 60 to 120 mils of blood per beat. Okay, is normal. So there's 3 things that factor in how much blood is going to be pumped. Okay, the contraction of a ventricle, the preload, and the afterload. So those are the 3 things, okay? So stroke volume is the volume of blood pumped out of the heart with each beat, and it's affected by contraction of the ventricle, preload, and afterload. Okay? So we'll talk about preload first. So preload, well, let's talk about the left ventricle, okay, is how much blood is in the ventricle before contraction. Okay? So we call this the EDV, or the end diastolic volume. Okay, so the amount of blood that's in the ventricle before contraction. Afterload is the pressure required to open the aortic valve. Okay, so in order to understand this one is think about someone pushing against a door that you're trying to get through. Okay? You need to exert more force or more pressure against that door in order to overcome the person on the other side. Okay? Similar type of thing with afterload. If you think of the left ventricle and the blood trying to get through the valve into the aorta, okay? There needs to be enough force in order to open that valve against the pressure of the blood that's already inside the aorta. Okay, so that's what's going on. It's not just an open area, there's actually blood in there. Okay, so it is the force required to open the aortic valve in order to be pumped through the rest of the body. So that is the afterload. This has been a video log from mastermedics.com.
プリロードとアフターロードを説明したね。ちょっともう一本見てください。
Hey guys, this is a short video on the key concepts of end-diastolic volume and systolic volume, stroke volume, venous return, afterload and preload. Okay, so these terms are very important to understand in order to comprehend the concept and relations of blood pressure. So let's start. In this pic you can see 4 stages, and in stage 1 the bottle is in the relaxed state or in diastole and it is being filled by water. This water is the venous return which is coming from the tissues. Now, in stage 2, the volume of water present by the end-diastole is the end-diastolic volume. This volume produces a load on the walls of the bottle which is called the preload. Next is stage 2.
Oh, why preload is important? Because preload makes how much volume is stored to filled in this the pumping chamber. So how much volume is stored to the preliminary. That is also important to how much exhaust once. Then when it is pushed, contracted, this preliminary stored volume is also important. And then of course this resistance or this pressure after load is also important to make this power.
The bottle gets contracted, as a result of which the water is pumped out. This pumped out water is basically the stroke volume, and the load against which the water is pumped out is the afterload. Finally, we come to stage 4, where whatever volume of blood is left in the bottle is basically called the end systolic volume. This is about it. So now just replace the word water with blood and bottle with ventricle, and you're good to go.
ね、ちょっとだからこのプリロードとアフターロード、もちろんストロークボリュームっていうのももちろんインポータント。これ difference is the stroke volume. How much volume is out, pulled out from here is also important. But these 3 factors is very important for the pumping functions of the heart. っていうのはここで言われました。いいね。この、スターリングズ・ローっていうのは、このスターリングっていう、イングランドのメディカルドクター is showing about this. エナジーエフィシェンシーはだから、ボリュームと、プレッシャーのサイクル、ボリュームプレッシャーサイクル is here, and this inside part is a working of the heart muscles. So this heart muscle is about the 10 watt が、運動が10ワットで、and the myocardic oxygen consumption が the energy equivalent で about 60 watt なんで、so therefore the energy efficiency はこの実際のactual workload is looks like this, but energy is consumed like this. So therefore, the energy efficiency about 10 or 20% in the heart muscle. ということですね。それはどっか カーディアックアウトプット、ストロークボリュームっていうちょっと説明を見ますか。
Cardiac output is the amount of blood pumped by each ventricle in 1 minute. It is the product of stroke volume, the amount of blood pumped in one heartbeat, and heart rate, the number of beats in 1 minute. An increase in either stroke volume or heart rate results in increased cardiac output, and vice versa. For example, during physical exercises, the heart beats faster to put out more blood in response to higher demand of the body. It is noteworthy that the ventricles do not eject all the blood they contain in one beat. In a typical example, a ventricle is filled with about 100 milliliters of blood at the end of its load, but only 60 milliliters is ejected during contraction. This corresponds to an ejection fraction of 60%. The 100 milliliters is the end diastolic volume, or EDV. The 40 milliliters that remains in the ventricle after contraction is the end systolic volume, or ESV. The stroke volume equals EDV minus ESV and is dependent on 3 factors: contractility, preload, and afterload. Contractility refers to the force of the contraction of the heart muscle. The more forceful the contraction, the more blood it ejects. Preload is related to the end diastolic volume. Preload, by definition, is the degree of stretch of cardiac myocytes at the end of ventricular fill-in. But since this parameter is not readily measurable in patients, EDV is used instead. This is because the stretch level of the wall of a ventricle increases as it's filled with more and more blood, just like a balloon. The more air it contains, the more stretched it is. According to the Frank-Starling mechanism, the greater the stretch, the greater the force of contraction. In the balloon analogy, the more inflated the balloon, the more forceful it releases air when deflated. Afterload, on the other hand, is the resistance that the ventricle must overcome to eject blood. Afterload includes 2 major components: vascular pressure. The pressure in the left ventricle must be greater than the systemic pressure for the aortic valve to open. Similarly, the pressure in the right ventricle must exceed pulmonary pressure to open the pulmonary valve. In hypertension, for example, higher vascular pressures make it more difficult for the valves to open, resulting in a reduced amount of ejected blood. Damage to the valves, such as stenosis, also presents higher resistance and leads to lower blood output.
っていう話ですね。はい。ということで、これちょっと、これはさっき見たし、で、次はシミュレーションですね。コンピューターシミュレーション。で、several weeks ago, I asked you to find this one single cells mechanical feature is mechanical feature means some the K とかね spring constant or viscosity is necessary to measure. I asked. So because one reason is to this kind of simulation, heart simulator making, each part is a single cell. So therefore the single cell's mechanical feature should be measured and it makes some these tissues and the organs, and then you can simulate movement of the heart. でそれは例えば、これは、マルチフィジックスシミュレーションでこの making this kind of これ single heart cells simulation とか、このポンピングのシミュレーションとかね This kind of simulation is made, and then the heart simulator is one functional topic about the simulating the total of these heart functions. So you can see this video. 例えばリアルタイムハートビートシミュレーター visualize pulsation and disease on the laptop PC とか今ちょっと見てますか?
This simulator can represent the complex pulsation of the heart. It is being developed by a group including members from the National Cerebral and Cardiovascular Center and RIKEN. Until now, simulating heart pulsation has required huge amounts of computing, done by supercomputers or offline. But this new system makes it possible to visualize heart pulsation on a notebook PC in real time by applying computer graphics technology.
従来の方法というのは力学に基づくシミュレーション方法だったんですけど、私たちの方法は全く新しくて、形状制約に基づくシェイプマッチング法という技術を使っています。簡単に言うと、心臓モデルを7000程度のパーツに分割します。で、各パーツを独立して収縮させます。で、収縮したパーツの矛盾がなるべく少なくなるように心臓形状全体を検査するというのがこの手法の主なところですね。こちらでは心臓の3次元モデルで、これは CT 画像から領域抽出をすることで作られています。患者さんの3次元モデルです。中に心筋繊維装甲がデザインされていますで、こちらのグラフで収縮のタイミングを指定することができます。で、通常は、心房領域に収縮がまず入って、でさらにそれに一時遅れて心室に収縮が入ります。
Because the heart model runs in real time, it's possible to deform the heart by applying tension and to observe cross-sections. Additionally, heart attacks can be simulated by stopping the motion and painting a region. This also makes it possible to create virtual heart disease.
まずは医療現場で何とか適用していきたいと考えていて、第一のターゲットは医師と患者間のコミュニケーションを支援するところです。で、もう一つは若手医師の支援です。若手医師の教育の支援ですとか、単純に処方療育の支援にも使いたいと思います。
The remaining issues that need to be overcome include reducing the complexity of creating individual patients' heart models, as well as finding ways to handle complex patterns such as ventricular fibrillation. Digging for news.
これは日本の in Japan の about 5 years ago ぐらいのやつですね。他にも this kind of similar project is also in USA or in Europe. For example, 例えばこの Living Heart Project ですね。見てみますか。
The Living Heart program from Dassault Systems Smulia is a project intended to create realistic simulations of human heart function so that they can be applied to medical practice, designs of new devices, using the best physics available to solve real-world problems. It's a project put together by Dassault Systems to bring together collaborators from academia, medical research, clinical practice, regulatory bodies, to take on the biggest challenge in medical science right now, and that's cardiovascular disease.
Our technology enables our customers in the life sciences world to perform these sorts of simulation, but it's with our technology, along with their knowledge and our experienced engineers, that'll allow us to deliver a solution.
I got to see the 3D tablet demonstration in the cave, and I was blown away. I think these are fantastic teaching tools that medical schools would love to have, as well as the clinicians. If they could study a patient's heart in 3D glasses, rotate the model, they'll be much better aware of the disease and how they may cure it.
So within science, there are three traditional pillars of scientific discovery. There's experiment, there's theory, and there's simulation. And there's a new emerging field, which some people refer to as data science. The Living Heart project is really a good example where we need to take many of those different components and integrate them together and make them work together. Every researcher who sees the work, the progress we've made so far, gets excited, wants to work with us, sees the potential for future innovation and future research directions. It's an exciting time for us.
というのはこういう US プロジェクトこれですね。これ確かイタリアだと思ってちょっと見てみますか。なんかリアリスティックハートですね。バルブのムーブメントもすごいリアリスティック。 バルブの動き、これシミュレーションだっていうんですけど。とかあります。いろんなの。はい、ということで、いいですか ?OK。Today's content is